Well, because this one has a camera. It doesn't have to be pretty as long as, you know, you see that the whole point is that I need some evidence that I'm a decent teacher. And sadly, all of you signing a petition saying, Bob is so great, please hire him, University of Ohio, won't do it. So,
I'll call them if you want me
I appreciate you putting up with that.
I thought that all.
Okay.
Yeah. That's what I'm trying to get
There is quiz, which we have done. All right. Nonlinear regression functions, binary dependent variables. It's not as scary as that sounds. We have already learned how to handle data that is categorical when it's on the right-hand side of our regression equation. Sometimes you want to include gender, or whether something is true or false, what state someone lives in your regression as one of the independent variables. Those things are not numbers. 1/2 Connecticut plus 3 Montana doesn't mean anything. But we learned that we can include categorical data in our regressions by making them dummy variables. So if you wanted to include gender, you could code female as 1, male as 0. Well, now they're numbers. You can include them in your regression, and Stata will give you some coefficients, no problem. So if you want to have categorical data as the dependent variable, as your y, as what you're trying to predict. You're trying to predict whether something is true or false, up or down. Whether someone does or does not own a house would be an example. You can do the same thing. You can code it just as a dummy variable, 0 or 1, and then run a linear regression, no different than you've done before. You can do that. Sometimes it's okay to do that. Sometimes it's going to cause you problems. What did I put? There we go. All right. These are some more examples of the kind of categorical data you might want to include. Now, I want to make the point that tonight we're only going to be talking about binary categorical data, where there are only 2 categories. Now, you know, with the dummy variables we've included on the right-hand side of regression, we've included variables that have more than 2 categories. For example, 50 states, you would include 49 dummies. But here we're only dealing with 2 categories. Did an individual attend college? Yes or no. You could code someone who did as 1, someone who did not as 0. Does an individual have health insurance? Did an individual vote in the last election? They all take the form of true, false. So you would code them as either 0 or 1. Now we're going to look at 2 different ways to handle that kind of data when it's when it's a left-hand side variable, a dependent variable. The first is what we've been doing since the beginning of the semester, just ordinary linear regression, the way I described before. The second way is probing. Now, also there is one more method, LOGIT. I asked my dissertation advisor this afternoon, how do you pronounce that? Because I've heard logit, logit. He says the correct way to pronounce it is logit. Therefore, the correct way to pronounce it is logit. Logit and probit, these two methods produce, for all practical purposes, identical results. I have been told that there are some very obscure cases where you want to use one and not the other, probit and not logit, logit, not probit. I've never run across them. In any case, you're likely to ever see logit and probit. Use whichever you want. Certain disciplines tend to favor one more than the other just by habit, but it really doesn't make much of a difference in almost any cases. Okay. Now, this is the linear model that we've been looking at. When you code your dependent variable, your y is either 0 or 1. Does someone own a house? 0, no. Yes, 1. You can run a standard regression on that data. Here is an example of that plot. Each little circle is one observation. This is whether a person has ever, at any point in their life, been married. Age across the bottom. And you see, if the answer is yes, it's coded as 1. No, coded as 0. There are no values in between. It's either one or the other. Now, if you run that regression using standard stata command, regress married on age of female with robust standard errors, you get these coefficients. Age plus 0.04, the female dummy plus 0.09, and a constant of -1, roughly. Okay. Given that you have run that regression, you have that intercept, you have those coefficients, how do you interpret the results? The coefficient on age, you interpret it the same way you always have, controlling for gender. A 1-year increase in age associated with a 4.6 percentage points increase in the probability of ever having been married. The coefficient on the female dummy variable, controlling for age. Women are 9.1 percentage points more likely to have been married than men. Nothing really new there. Now, let's plug in some numbers and see if we can make a prediction, see if we can use this regression. Someone who is 40 years old and female, what is the probability they've never been married? Well, you just plug them in. The prediction is -1.02 plus 0.046 times age, 40, plus 0.091 times 1, because this person is female. And the answer you get is 0.925. 92.5% chance. Makes sense. But now let's try to do the same thing with different data. What is the predicted probability that a 20-year-old male has ever been married? We'll just plug in the numbers again. -1.02 plus 0.046 times age plus 0.091 times the dummy variable, which is coded 0 for male. And you get an answer of -0.09. Well, if this means there's a 92.5% chance that this person's ever been married, then this means there's a -9% chance this person's ever been married. What does a -9% chance mean? It means nothing. Exactly correct. Now, if you use a standard linear regression with binary, categorical, dependent data, well, mechanically you can do it. You can code yes as 1, no as 0, owns a house as 1, does not as 0, and you can make stata run the regression. Sometimes it'll give you a meaningful answer. If you're sort of in the middle of the range of your data, it'll give you an answer that's not unreasonable. But when you get to the tails of your data, this method is going to break down. It'll give you answers that either are ridiculous or impossible. Let's look at this example that I made up. Hope it'll help you with the intuition. You're interested in what kind of cereal, what brand families like. This assumes that everyone in the family likes the same kind of cereal. Nobody's fighting with each other. And every family likes one kind of cereal. And the only two cereals that exist are Fruit Loops, my favorite, and Cheerios. And you want to predict which cereal families like based on their income. So you have data. Here is income in thousands per year. If the family likes Cheerios, you code it as 0. If they like Fruit Loops, you code it as 1. Now you can see an obvious pattern. At high income levels, families tend to prefer Fruit Loops. At low income levels, most of the families, although not all, like Cheerios. So there's an obvious relationship of some kind between family income and cereal preference. Let's run a standard regression. We get this blue line. Now, we've seen standard linear regressions where the line doesn't fit the data very well. Even the line of best fit, well, best can still be pretty terrible. Obviously, this line does not fit the data terribly well. But still, this is the line of best fit. Okay. Notice here, there is no family in your survey data with an income of 70,000 exactly. So let's say, given this model, you want to find out what is the chance that a family making 70,000 likes Fruit Loops, for example. Okay, do what we've always done. Go up, you go over, and this model predicts 0.5. Well, you've defined Cheerios as equal to 0. And you said that in this model, Fruit Loops is equal to 1. You haven't defined any other numbers. What is 0.5? Anybody want to take a stab at interpreting that? What would be a common sense way to derive meaning from that? Yeah.
It's the probability that they like Fruit Loops.
The probability that they like Fruit Loops. Yeah. That's an obvious common sense way to interpret this. This family has, you predict, a 50% chance of liking Fruit Loops. And just looking at the data, it makes sense. They're in the middle of the income range, so we probably should fall in the middle of the cereal preference as well. Just eyeballing it, it looks reasonable. Okay, let's say you want to do some more predictions. $120,000 income. Okay, what cereal do they probably prefer? What prediction are you going to make about the probability that they like Fruit Loops? Well, up and over, and you get 1.3. If you defined this as a probability of 0.5. You're interpreting the number as a probability, which in this area seems reasonable. What is a probability of 1.3? What does that mean?
130.
I'm sorry, I couldn't hear you. It means nothing. You're right. Probability of 1.3 is meaningless. It means that there's 130% chance that this family likes Fruit Loops. Contrary to what you hear athletes and their coaches say, you can't give more than 100%. So 130% chance of this happening it's meaningless. It doesn't make any sense. Let's look at another one. This family, very low income, income of 5,000. What kind of cereal do they like? Do the same thing, round and over, and you get a predicted probability that they like Fruit Loops of -0.2. So if there was no chance that they liked Fruit Loops, well, the probability they like Fruit Loops is even less than that. That doesn't make sense, again. So, using the linear model for categorical dependent data, sometimes it'll give you a number that looks reasonable, and sometimes it'll give you a number that's flat out impossible. And we'll get to this a bit more later, but notice where it does each of them. If you're in the middle of your data, this area, the predictions are at least possible. Will kind of work. At the tails of the data, that's where it completely breaks down and gives you not just unreasonable, but impossible results. So, what to do? When we've seen data before that just doesn't fit a linear model, that the line of best fit still doesn't fit well, we've transformed the data. Taken a log, polynomial, and we've even done that on the left-hand side. Last week we talked about, was it the week before, that you can take the log of your dependent variable, log of y. Sometimes that makes it fit the data better, and that's fine. Well, the log is just a function. You take y, stick it to the log function, you get out log of y. Under some circumstances, that can make the model fit the data better. Well, it'd be nice if we had some function that could transform the y's such that you wouldn't have this problem of results greater than 1, or you wouldn't have this problem of results less than 0, probabilities that are not possible. It'd be really nice if you had something like this. Notice this in the middle. Now, the slope is sort of like the linear regression model, not too different. But here at the tails, it's very different. Instead of a line that goes out to plus infinity and negative infinity, this asymptotically approaches 1 or 0. But it never goes above 1, never goes below 0. Okay, visually, that looks like it would work. But what kind of function is that? It's this. This is the standard normal distribution. This is the cumulative standard normal distribution. At each point here, at each x, this line shows you the probability that a value would be there or to the left. It just adds them all up. So it's a different way of showing really the same information. This, no matter what x you give it, -1 billion, +100 trillion, the y will never be below 0 and will never be above 1, because the area under this curve is 1. Okay. The probit model uses the cumulative normal distribution as a way to transform your dependent variable so that you never have to deal with the problem of results that don't make sense because probabilities can't be more than 1 or less than 0. Now, the function that you use to transform the data is called a link function. And there are multiple different link functions. This is the probit link function. Logit has a mathematically different link function that does the same thing. Now, in probit regression, how it mathematically finds the coefficients, the betas, is different. It uses maximum likelihood estimation, which is beyond this class. I'll give you a little flavor of it later. It's just a different mathematical technique to accomplish the same thing, to find the best fit. Okay, now, before I get to this one, talk just a bit more about what a link function does. Here, you have probabilities. It can go from 0 to 1, be anything in between. But linear regression can produce a prediction that's any real number. Anything from negative infinity to positive infinity. The linear regression model and so far this is the problem, because your regression may predict, for example, a negative number, like the probability of negative 0.2, or a probability that's greater than 1. Well, you can't have negative probabilities or probabilities greater than 1. So since you're going to get potentially any of these numbers out of your regression, you need some way to map, to translate the real number line, this range of numbers, onto this range of numbers. A function that will translate between the range 0 to 1 and the whole real number line. So that way, when you run the regression and it gives you a prediction of 115, it's not a garbage result. It's a number that can be, running through the function the other way, translated into a probability that is between 0 and 1. Now, for the probit model, how you do that, how you take the regression result and convert it back into a probability is this. This is the standard normal curve. Now let's say that you get, actually it should be x times beta, of negative 1. Well, what does that mean? If your y value is negative 1 in a probit regression, well, you can't interpret that as a probability because you can't have a probability of a negative number. But in the normal distribution, negative 1 is, you can interpret this as a z value. The area under the curve from negative infinity up to negative 1, the green area, that is the probability that your outcome variable is success, takes on the value 1. Because the area under the curve represents the probability. The area, total area under the curve is 1. If your x times beta equaled 2, the probability is this area. So the y value that you get after you do this transformation, it's just a z-score. If you want to translate a z-score into a probability, you can look it up in a table. I recommend you don't. We have software nowadays. Stata can do it. Google z-score. There'll be a calculator. 100 of them will pop up that will convert z-scores into probabilities. Okay. So the probit function is the link function, but it's just a way to transform the variables to express the data in a different form that makes it fit the data better. It doesn't change the information content, but it fixes the problems of linear regression, of untransformed data, giving you results that don't make sense when viewed as a probability. Now, for the marriage data that we looked at before, this is an example of both types of regression superposed. Excuse me. Now, you can see that here in the middle, well, the slope of the probit regression and of the linear regression, they're not too dissimilar. If you plugged in 30, you get a similar prediction. You can't see it so much up here because the graph is truncated, but down here you can see it a bit. When you get in the tails of your data, that's when the predictions tend to diverge. If this linear regression line continued, well, you see here it's already below 0. If you interpret the linear regression intercept as a probability, then someone with at 0 age would have, what would it be, -2 probability of having been married. But the probit model, it levels out and never crosses 0 into a negative number. So, the advantage of using just plain old linear regression is it's really easy to interpret the coefficients. You've been doing that all semester. The disadvantage is if you get out in the tails of your data, it's just not going to work. With probit regression, you don't have that problem, but it makes it harder to interpret your results. If you only have one right-hand side variable, then you can interpret it as a 1-unit change in x leads to a beta change in the z-score of y. So, interpreting the results, the coefficients, if you have more than one right-hand side variable, which you usually will, that gets even more complicated. Because the slope, remember, the slope is not constant. Here, the slope looks like, 0.7, something like that. But as you get down here, the slope shallows out. So the marginal effect is going to be different based on the age. So, when you do a probit regression and you're looking at the coefficients and you want to know what do these mean, there are a couple things that are easy to do. You can look at the sign. If it's positive, that means when that variable increases, it'll tend to be associated with a higher probability of the outcome. It makes it more likely. If it's negative, it means when that variable goes up, it'll make the outcome less likely. So you can tell the direction of the effect really easy. Also, when you look at your stata output, it's really easy to see if it's statistically significant. Stata tells you. But when you go beyond, well, if it's not statistically significant, that simplifies your interpretation right there. But if it is significant, the direction of the effect, easy, look at the sign. But the magnitude of the effect, basically you can't, in any practical sense, just look at the number and come up with a real world interpretation. This is an example. Probit regression, person married on age. Now, I mentioned that with Probit and also Logit, the way it finds the coefficients mathematically is a little different. It uses maximum likelihood estimation. If I have time, I'll show you just a bit of what that is in a qualitative sense and why it's necessary. This is part of that estimation process. You don't need to worry about it for this class. I have a link to UCLA website, I think I already posted it to Blackboard, where they annotate the Probit stata output. So if you're interested in the details of what some more of these things mean, that's there for you. Here, this is the coefficient, age 0.15. Oh, also, I should point out pseudo r squared, 0.28. Why does it say pseudo? Because the traditional r squared, we've come to know and love, you can't calculate that in a Probit regression. A lot of people have tried to create substitutes for it. This is one of them. It sort of accomplishes the same thing, but just be aware that this is not really an r squared. It's something similar. Okay, so you can see here the coefficient on age is 0.15. It is positive, and it is statistically significant. Just looking at that, well, first it is statistically significant. That's easy to see. And you can see that the coefficient is positive. That tells you that increasing age will make the outcome more likely. The older someone is, the more likely it is that they've been married. That makes sense. Here, if you just do the straight linear regression with robust standard errors, well, again, age is statistically significant. You get a coefficient of 0.04 and an intercept of negative 0.9. You're going to run into the same problem. For very high ages or very low ages, this is going to give you probabilities, predict probabilities that are invalid. Now, comparing the two. Here, we're just having stata convert the Probit statistic into a probability. Here you can see for someone 20 years old, it predicts a 3.4% chance they've been married. For someone 22, it goes up to 6.3. For someone 30 years old, 37% chance. For someone 32 years old, almost a 50% chance that they've been married at some point. That's with Probit regression. These are the same numbers that we get from straight linear regression. Let's look at them together. Predicted probability, age 20. This is 22. You see the difference. For linear, 0.09. For Probit, 0.03. The same difference of 2 years from 30 to 32. Well, with a linear model, that's the same difference. But the probit model, it goes way up. Shows that there's a larger increase in the probability you'll be married between these 2 years than between these 2 years. Probit captures that. Linear does not. Since it's so hard to interpret the coefficients, you can use the marginal command instead. Now to know the marginal effect, to know how much, not just the direction, but how much a 1 unit change in your independent variable changes the probability of your dependent variable, you need to tell it, well, for what value of your independent variable. As we see here, if you're dealing with this age range, it makes a big difference. This age range makes a smaller difference. It's a convention. Frequently people will just quote the effect at the mean of those values. But that doesn't help you if you're not examining the mean of those values. You can use the marginal command. The mean age of the sample is 29.4. Here it shows the command. And here, this does give you something you can interpret. For people who are of the mean age, a 1 year increase in age is associated with a 5.5% percentage point increase in the probability of being married. So that can be interpreted. When you have multiple right-hand side variables, it's going to get really hard to interpret. I think that's beyond the scope of this class as well. But you can still use it for prediction easily. Tell you what, why don't we take 10 minutes, actually make it 12 minutes until 25 past, and then I'll talk about logit and some of the differences between the two and how to interpret them.
The Mayan bias.